GAC, AP Stats. Hope you're having a fantastic day today. This is Monday morning, and we are on to Unit 7. The Unit 7 we're going to talk through is our AP Stats test. All of our tests we're going to dominate here, and we're going to go through that Unit 7. I'm going to go as far as I can because I know I've got students that are coming in a little bit later, but let's get started, and we'll go through those together. All right, so let's get kind of rolling here. Yes. Okay. So we're on section 7, chapter 7 here. And what I'm going to do is I'm just going to kind of talk through a couple of these, make sure that we go through all the logistics of what's expected to be put on these tests. Because I know there's a lot of question marks regarding what's expected, what do we put down. And so I wanted to make sure that we hit on that accordingly. So let's go through those together. I'm going to do this. Thought I had this up and rolling, but I'm a little off here. Let me get this together right here. One thing that I would make sure of is as you go through this podcast, make sure you identify the specific forms of what you need to put down for each test. Not even just what you put down, but then also the specific tests and the wording within each. That's kind of the big thing that I'm noticing is that the wording of each of these is unique. And to be able to identify what one goes with each, something that's very important. So just something to kind of keep in the back of your mind going forward there. All right. So we're going to go over these sections. Oh, I got them out of order. There we are. Okay, perfect. So as we go through this, one thing to identify is the difference between confidence intervals and tests. So as we look at confidence intervals, things that we were looking for before, things like 99% confidence interval, talking about whether we're doing a 1 or 2 sample test and whether it's a confidence interval or a test based upon the wording that's there, and using that wording to then say, is it a proportion or a mean? And so these 3 questions were the 3 things that we kind of were talking about on the sections before we kind of broke away for the year. So as we look at some of these examples, let's look at some of the state, plan, do, conclude problems and what we are expected to do for each. All right, so let's look at example 1. It says Chicago-style popcorn is a type of popcorn made by mixing together cheddar and caramel popcorn. True Chicago-style popcorn is composed of at least 40% of caramel popcorn. A new popcorn shop advertises that they will be selling Chicago-style popcorn. To test this claim, a popcorn lover takes a random sample of 500, and I like to underline things just so you know, and finds that 183 kernels are caramel. Does the data provide convincing evidence? Here's the thing. If you see that, that's always a test, okay? Just a heads up that the shop is not selling true Chicago-style popcorn. And then state, plan, do, conclude. So as we go through this, the one thing to remember is within our state part, what we want to do is we want to identify what the variable of that we're trying to look for is. So the fact that the convincing evidence, true Chicago-style popcorn related to the caramel, that's up here, is we're saying that P in this case is the true proportion, and we want to identify this. The true proportion of caramel popcorn, I would say you could say caramel, that is popcorn in Chicago style, or you could just say of popcorn that is Chicago style. And really that just means that this is like the caramel thing that's there. Okay? So as we look at this, remember with every test we have a hypothesis. Within the hypothesis, traditionally what we're going to do is show that with a P is greater than, less than, or equal to, that's there. So our null hypothesis is what they state. The fact of the matter is that the proportion must be 0.40, where the alternative, remember in this case, we're saying, does the data provide convincing evidence that the shop is not selling? So if it's not, if it's greater than 0.4, then we would say that we're okay. But if it was in fact less than 0.4, we would say that it is not in fact Chicago style popcorn. So we put that there. This is our state part. We, again, say what is P, and then we have our null and we have our alternative. Now, within the plane phase, one thing to remember, too, is we've got to find what our P hat value is. Sometimes they'll give it to us, but in this example, we have a random sample of 500, and 183 out of 500 is our proportion. So our proportion, when plugged into a calculator, is 0.366. So now for our plane phase, we're looking at a one sample. And since it's a proportion, we have a Z. And we're not a confidence interval, but we're in fact a test. So one sample Z test. Now, our next part that we want to state is you want to make sure that we identify the random condition. And a lot of times we look for the normal condition as well. But with the random, it was easy because it's just a random sample of 500, right? Set it in there. Random sample, and I would actually write this out. SRS is good, but just in case, really write that out. The next part that we want to state too is the normal condition. Does it say anything about the normal condition? I don't see it over there. I don't see the normal condition. Like it doesn't. Well, okay, yeah. So with the normal condition, we know that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10 for proportion. So we simply just plug it in. So we say, all right, 500 times 0.366 is greater than or equal to 10. Actually, write that out there when you do it. And 500 times 1 minus 0.366, which is failing, that would be 634. Yeah, 634. And that too is greater than or equal to 10. So what we would do there is just simply plug it in, and again, make sure you put what the total is on there. But we can say that this does in fact approximate this as normal. So once we go to the do phase, we want to make sure we throw a little picture in where the middle value always corresponds to what we assume to be true, which is our null hypothesis, 0.40. And then the 0.366 comes into play by saying, okay, this is 0.366. And what we're trying to do is identify what is the area, because we're doing less than 0.366, what is the value that's less than 0.366? This is called our p-value. And remember that if it was not equal to, you would simply do the mirrored version of that other side, which is just simply multiplying this by 2. Once I get to this point, you could in fact go to your z-score by saying z is equal to your estimate minus your parameter divided by standard deviation, which would be 0.366 minus 0.4 divided by the standard deviation, which, by the way, the standard deviation is different than, you have to figure that out with a proportion, doing the square root of p times 1 minus p divided by n, right? And so you would just simply plug in what the proportion is. In this case, it would be 0.4 because we assume 0.4 to be true. And so what we would do is have 0.366 minus 0.4 divided by the square root of 0.4 times 0.6 divided by 500, which is my simple random sample. So once we do this, we get negative 1.55, which means this is the z-score, which means that we are negative 1.55 standard deviations to the left of the mean. Now, in going to the z chart, right? Going to the chart there, you could identify what the area is by going negative 1.55 standard deviations and then just finding what the area is to the left of that. But maybe something a little bit easier would be to go to normal CDF. And I just want to show you, I won't do this every time, but I just want to make sure I show you that there is a difference. You would just say lower, comma, upper, comma, mean, comma, standard deviation. And then afterwards, you would just put normal, CDF. And then this would be, right here, the lower would be negative large number, negative infinity, negative 99999, comma 0.366, comma, mean, which is 0.4, and then comma, my standard deviation, which is what I got from up here, that I would put in right here. So 0.4 times 0.6 divided by 500, and whatever I got here, you could just simply plug in on this spot. And when I do that, I get a p-value that is 0.063, okay? So that right there is our p-value. And again, this is sufficient work. You don't choose one of these, right? Choose either this one or choose either this one. When you plug that in, either one will work. Just make sure you establish context down here, okay? That's the big thing. And again, the big thing also, so this is, remember, this is mu. This is from a sampling distribution. So mu of x bar is my mean, and my standard deviation, I'm sorry, not x bar because we're talking about proportions, p hat. And then standard deviation of p hat would be my standard deviation of my sampling distribution, which is what, these are what we plug in for here and here. But I just wanted you to see what that would be there, okay? So the big thing to note is, like, be very careful. I've seen a lot of us that have messed this up. So when I state this, right, we say because P is equal to 0.063 and it is greater than our alpha, which is equal to 0.05, we can't say that that means that the null is true, okay? But what we can say is that we just don't have convincing evidence. So we would just say we do not have convincing evidence to reject the null which states that the store is not selling Chicago style popcorn. Again, am I saying that they are selling Chicago style popcorn? No, I'm not. I just don't have convincing evidence. All I'm saying is that we do not have convincing evidence to reject the null, which states that the store is not selling Chicago style popcorn. Remember that that's the crux of it. To say that that this is definitively true, if this P was less than 0.05, we would say that they are in fact not selling Chicago style popcorn, and we'd have convincing evidence on that. However, we can't, when we have a 0.063, which does not reject the null hypothesis, we can't then say that the null hypothesis isn't true. We just say we don't have convincing evidence to reject it. So just a difference there, a little bit of a tweak, something important there as we go through, okay? All right, so with that being said, let's keep going because we're going to rock and roll. Hopefully that kind of established where we're headed here. This time we're going to look at this. Last year, an AP Stats class spent an average of 25 minutes a night on their homework, okay? All right, their teacher randomly completed 30 of her students this year to see if this average had gone up. The sample had a mean of 32. So, by the way, from the sample, this is from my sample, okay? So this would be my estimate. So this would be my X bar that's here, okay? So that equals 32. That's the average. And a standard deviation of 11 minutes. So there's our standard deviation from our sample, right? Is 11 minutes. Okay. That's important stuff to kind of get down there. Does the data provide convincing evidence? Again, that means it's a test. Those are key words. The AP Stats student spends more time on homework per night this year than last year. Well, let's talk about, since we're talking about mu, and we've only got one variable, this mu variable we would represent as the average, the true average or true mean, time the students spend on homework, okay? All right, again, we have our null and we have our alternative. This time we're talking about our true mu. So where true mu is 25, and we're saying, does the true mu, is that going to go up from 25 that's there? Okay. Since we're talking of one sample, we'll talk a one sample t-test. Okay. And specifically for mu, and you could put that down. You don't have to. First thing, our random condition. It's random because there's a random sample of 30. Sample of 30. The normal condition, here we go, number 2. Notice I am not saying independent, though it might be good just to state independence. Might be good to show that. It's not required, at least in terms of here. Now, here's what I would say. If they ask for specific conditions, like that's one specific question, put independence there. In fact, I would even just continue to put independence, especially if you have that time that's there. So just something to, just in case, okay? So this does passes the large counts, which means we can approximate this as normal. That doesn't mean it is normal. That just means we approximate it as normal. It's large enough to do that there, okay? So again, like we said earlier, we assumed 25 to be true. But we took our X bar, which was our 32, which is over this way, and we said with this 32, by the way, I didn't do this last time. Might be good just to kind of put this here, just in case on that. So we got our p value here, okay? So plug that in. You could also do your t, which is t equals your estimate. Minus, so 32 minus 25 divided by my standard deviation, which is s of x over square root of n. You could do it as that, but and then go to your chart with it, which is your t chart there. However, we could also do, since we're talking about t here, we could also do our TCDF. Okay, so we could do our TCDF here, where we go and we do TCDF. Lower, upper, and while I'm pulling that up, I kind of wanted to show this one here before I kind of keep going, because this one is a little bit different. But we get our P. Our P is 0.0008. And again, we want to make sure lower, upper, mu, standard deviation. And really, this is mu of x bar and standard deviation of x bar there. Okay. All right, sampling distribution, that's there for it. Okay. So just so we know where the stuff is here, if we did go to second vars here, this is our normal CDF, and then you see right here, we stay away from the PDF, at least for TPDF and normal PDF, but we could go to the TCDF, and there's our lower and upper. Now, here's where it becomes a little bit different. Because now what we have is our degrees of freedom. There's not really so just a little different, where like before we had, actually, I don't think you can see my screen. Like right here, this is what we did with normal CDF, right? Well, it's actually built in here where we do now our degrees of freedom for our TCDF. And remember, our degrees of freedom is our n minus 1, or in this case, 30 minus 1, which is 29. Okay? So 29 is our degrees of freedom. So we just simply put in TCDF, our lower, which is 32, our upper, which is a large number, 99999, and our degrees of freedom, which in this case is 29. But notice the mu and standard deviation. If you wanted to find it, mu of x bar is still 25. And then the standard deviation of x bar is s of x over square root of n, which is 11 over the square root of 30. Okay? But just again, just a heads up on that. One thing too, I put on my notes, a lot of times they still want you to solve for these two things, even though they may not state that. Yeah, right here, here we are. So make sure we still solve for the standard deviation and the mu of x bar. This is again on my sampling distribution. And once I get this, that's what I plug in to get this value of 0.0008. So we would say that because P is equal to 0.0008 and it is greater than our alpha level of 0.05, we do have convincing evidence to reject the null. Okay, that's kind of our first part. Now what we can do is then say, thus we can say, and you can just put this down, thus we can say that students within this year do spend more time on homework compared to last year. Notice the difference. I can, because this p-value is less than our alpha level, because that's the case, we can say that we do have convincing evidence to say that the students spend more time on homework this year compared to last year. That's, again, something just to keep in the back of your mind as we go through this together. All right, 7.2. This is where we start moving into our two-sample proportion and two-sample mean, okay? So we're going to kind of hit on that real quick. We'll walk through this together. So as we look at this, just notice a couple things. Does the data provide convincing evidence? It says two rival universities are both claiming that their graduates are more likely to gain employment within 3 months of graduation than those who graduate from the other school. A random sample of 500 recent graduates from College A revealed that 450 had employment within 3 months. So let's call College A 450 out of 500, which would be 0.9. Okay, so this would be like P hat 1. Okay, now let's look at P hat 2 here. It said that 400 of 342 out of 400, which would have gotten this for B, by the way. And I like to just make notes of this just in case. Hopefully that kind of helps me here. So once I plug the 342 divided by 400, don't see that there. Let me see if I've got. Just get this down on my calculator here. 342 divided by 400. I got 0.855, okay? So I got 0.855. All right. It then says, does the data provide convincing evidence that there is a difference? Okay, so big thing. When I see difference, that there's a difference of something and it's related to a test, which is what we saw here, right? We know that in this case, we're talking about something that's not equal to 0. So within my alternative, I know that whatever it is would not be equal to 0. And what we're talking about in this case is our P of A, or P1. You could say whatever you want there. We'll say P1 minus P2, where P1 is the true proportion of college graduates. And again, we're just defining our variables. Who got a job out of college. In college A. Okay, so we've got that. And then also our P sub 2, and I'll put that right over here. But this would be the same exact thing, and I would rewrite the same exact thing, but except in college B. Okay, so remember, we can't assume that there is a difference. Our null hypothesis must state that P1 minus P2 is equal to 0, meaning that there is no difference, right? P1 minus P2 equals 0 is traditionally what we start off with in terms of our null hypothesis that's there. Okay, so our plane phase, we have two samples. So we have a two sample, because it's a proportion, we call it a Z test. Sorry, the test for P1 minus P2, okay? Or we'll put that there. Now, the next thing is, our first thing is this idea of random. And this is where, again, we might want to just state that these are, especially because there's two, that they're independent. So we just will say that there's two independent random samples that were taken. Okay. You could also put the fact that one was a 400 and one was a 500. That would be fine too. The next condition we want to show is our normality. Can we approximate this as normal? So we know that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. And because of the fact that there's two of them, I've got to show this for both. So this would be like 500 times 0.9, 500 times 0.1. And again, I would write this out like in terms of like what's the answer here and here. And then the next one is 400 times 0.855 and 400 times 0.145. Yeah, that's it, 145. Make sure we show that both of these are greater than or equal to 10, okay? So we show those, and then we rock and roll on that, okay? Again, put those answers out there, but that's what we would expect there. Now, with a two-sided test, the one thing to remember here is that you don't actually have to show work, okay? So anytime that it is two-sided, we do not have to show work on this. If I wanted to show a graph, I could, where the difference, would be P1 minus P2, where the mean would be 0. And I could actually do like right here, if I wanted to, I could do P hat 1 minus P hat 2 to get my sample, which would be 0.9 times 0.855, which is equal to 0.045. Yeah. So 0.045 would be kind of what I would have them be over here, right? 0.045. And I would find this area. And then this would actually be mirrored on the other side because of the fact that it's not equal to 0, right? You don't have to show anything, though. Actually, you don't even have to show that part. The only thing that you have to show is how to do this on your calculator. So do this. I'm going to kind of show this on my calculator here now that we've got it on this side. And I'm going to show you how I got here in just a second, a little bit later. But I would get a p-value that's 0.039, okay? So because this is less than our 0.05, which would be good to put over here, we would say that because p is equal to 0.039 and it is greater or less than, my fault, wow, less than our alpha level of 0.05, we do have convincing evidence to reject the null, and then make sure we put a little context in there. What does that mean? That means that based upon this study, we do have convincing evidence to reject the null hypothesis. Therefore, we can say that there is a difference in the proportion of graduates who had employment within the 3 months of college for college A and college B, okay? Again, make sure you put that context there. Without that context, you'd have a little bit of a problem on that, okay? Cool. All right, let's do one more here. And let's do one more, and then we'll be going. All right, the next one, and then I'll go to our calculator. I'll kind of show you on that one too. For this one, this is, again, with means. Notice I have two samples, form A and form B. Does the data provide convincing evidence, which tells me that this is a test? Notice the little bit of a difference here, which is our alpha level, 0.01. So here we would want to make sure we have mu of 1 or mu of A. You could put whatever variable you want as long as you define it. And mu of B, define that too. So this would be the true mean score for A and the true mean score for B, okay? So we got our null and we've got our alternative here, okay? Where mu of A minus mu of B, remember we normally will set this equal to 0 because we've got two samples that are going on. Notice too, because of the fact that they gave me the means, this identifies the fact that it'll be related to means, not proportion, okay? Our alternative, mu of A minus mu of B. Now let's look at the wording here. It says, does the data provide convincing evidence that the mean score on form A was higher? So that means this would be greater than here. than the B version. So we would say that this is greater than 0, meaning that mu of A would be the larger value. So just like we did before, we have 2. We have a 2 sample t-test for mu of A minus mu of B. Okay, we've got our randomness. Yep, so we've got random samples. And we want to make sure we write those out, right? So we've got random in this case. So based on this, was it randomly assigned? Recorded the score. Oh, yeah, which were randomly assigned. Okay, so this was randomly assigned to versions of test. Okay. And then my last thing, I want to make sure I state the second thing, which is the normal condition. And because both of them are greater than or equal to 30, we would say that n must be greater than or equal to 30 to approximate this as normal. So for form A, you want to show for both of these, by the way. Form A would be 30 is greater than or equal to 30. So we're good there. And form B is 30 greater than equal to 30. So we're good there. So large counts passes. All right, so we're good here. Perfect. We're good there. And then we go to our do phase, which we'll wrap up at. So we'll have already said the 2 sample t-test here. And what we could say here is that P is equal to 0.078 or 0.098, my fault. And so what we've got here, good to see you. Merck showing up on the podcast. I love it. 0.098, and because that is greater than our alpha level of 0.01, we would say because, and you know, I mean, all of you know what we're doing here. Because P is equal to 0.098, and it is greater than our alpha level of 0.01, we do not have convincing evidence, and we just keep writing like we've been doing. We do not have convincing evidence to reject the null, stating that the scores from Form A were, in fact, higher than the scores from Form B. That doesn't mean that this is a fair test. It just means we don't have convincing evidence to state that Form A would have higher scores than Form B. So again, just a heads up there. That's what we would be looking for on that. And again, that's what we'd expect. Now, the last thing before we wrap this up here, the only other thing that I wanted to look at together was, let's see here. Let's see, gotcha right here. Okay. So what about the test? The only other thing I wanted to show you is when you go to your stats and you live in test world over here, the one thing to remember is there's a couple things to kind of identify. So especially the 2 sample stuff, the 2 samples t-test, we could plug in where we have our mean of sample 1, standard deviation of sample 1, and the sample size of 1, and then X bar, standard deviation, and sample size of part 2. We would then put in whether it's equal to, less than, or greater than. We would put not pooled in for these here, and then we would simply plug that in. For the z-test, when we go to 2 proportion z-test, I want you to see this here. You'll notice that the x1 and the n1 are a little different. Do not put in for the x1 right here, do not put in the proportion like 0.8 or 0.9. Put in like from the 500 one we just did, put in 450, and then the 500 is what you'll put in for N1. They do the proportion for you, but don't put the proportion in, like just put in the amount of successful, how many things were successful in the sample size. So 500 in for N1 and 450 in for X1, and go from there. And then we have sample 2, sample size 2, and then just do the same thing and then calculate and figure that out. The only other thing to kind of show you is when you go to your test 2, if you go to 1 proportion z-test, you could do that. And then also you could do your, sure, did I skip it? 2 sample t-test we saw. Oh, just the t-test. So if you just go to t-test, this is the one sample. So you could plug it in here, but make sure, again, you must show work when it's one sample. It's the two samples that you don't have to show work on there, okay? I recognize that right now you've got maybe some questions on the chi-square test, and we'll look at some of that stuff later, and we'll do kind of a part 2 podcast where we'll talk about chi-squared. We'll talk about the linear regression test that we got there, but before we do, we'll go to part 2 in a little bit later. All right, see you later. Happy studying. Bye.